The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, basically, the last few weeks we've been doing derivatives. Now we're going to do integrals. So, okay, so more precisely, we're going to be talking about double integrals. Okay, so just to motivate the notion, let me just remind you that when you have a function of one variable, say f of x, and if you take its integral from, say, a to b of f of x dx, well, that corresponds to the area below the graph of f over the interval from a to b. Okay, so the picture is something like you have a, you have b, you have the graph of f, and then what the integral measures is the area of this region. And when we say the area of this region, of course, if f is positive, that's what happens. If f is negative, then we count negatively the area below the x-axis. Okay. So now when you have a function of two variables, then you can try to do the same thing. Namely, you can plot its graph. Its graph will be a surface in space. And then we can try to look for the volume below the graph. And that's what we will call the double integral of a function over a certain region. Okay, so let's say that we have a function of two variables x and y. Then we'll look at the volume that's below the graph z equals f of xy. Okay, so let's draw a picture for what this means. I have a function of x and y. I can draw its graph. The graph will be, the surface with equation z equals f of x and y. And, well, I have to decide where I will integrate the function. So for that, I will choose some region in the xy plane. And I will integrate the function on that region. So it's over a region R in the xy plane. So I have this region R, and I look at the piece of the graph that is above this region, and we'll try to compute the volume of this solid here. Okay, that's what the double integral will measure. So we'll call that the double integral over the region R of f of xy dA, and I will have to explain what the notation means. So dA here stands for a piece of area. A stands for area. And, well, it's a double integral, so that's why we have two integral signs. And we'll have to indicate somehow the region over which we're integrating. Okay, we'll come up with more concrete notations when we see how to actually compute these things. But that's the basic definition. Okay, so actually, that's not really much of a definition yet. How do we actually define this rigorously? Well, remember the integral in one variable you probably saw a definition where you take your interval from A to B and you cut it into little pieces. And then for each little piece, you take the value of a function and you multiply by the width of the piece. That gives you a rectangular slice. And then you sum all of these rectangular slices together. So here we'll do the same thing. Okay, so, well, let me put a picture up and explain what it does. So we are going to cut our region into little pieces, say little rectangles or actually anything we want. And then for each piece, with a small area delta A, we'll take the area delta A times the value of a function in there that will give us the volume of a small box that sits under the graph. And then we'll add all these boxes together. That gives us an estimate of the volume. And then to get actually the integral will be defined as a limit as we subdivide into smaller and smaller boxes and we sum more and more pieces. Okay? So actually what we do, oh, I still have a board here. So the actual definition involves cutting R into small pieces of area, let's call delta A, or maybe delta AI, the area of the ith piece. And then, okay, so maybe in the xy plane, we have our region, and we'll cut it maybe using some grid. Okay, and then we'll have each small piece will have area delta A, or maybe delta AI, and it will be at some point, let's call it xi, yi, xi, and then we'll consider the sum over all the pieces of f at that point, xi, yi, times the area of a small piece. So what that corresponds to in the three-dimensional picture is just I sum the volumes of all of these little columns that sit under the graph. Okay? And then so what I do is actually I take the limit as the size of the pieces tends to 0, so I have more and more smaller and smaller pieces.